So, very welcome everybody, and we have as guest in our lecture now, Will Green. He's PhD student from the University of North Dakota, and he will comment. Sorry, I had it on my iPhone too. And he will talk about developing a robotic testing device for spacesuit joints. You may start your lecture, and to the audience again, please switch off your cameras and your audio. And afterwards, you have time for question and answers, and you can put it in the chat. Okay, you may start now.
Okay, sounds good. So like she said, my name is Will Green. I'm a PhD student at the University of North Dakota in the Department of Space Studies. I work in our human spaceflight laboratory. And so today I'll be presenting the robotic testing for spacesuit joints, particularly the design of the Mars joint tester. One second. Yep. All right. Okay. So overview for the presentation. First, I'm going to go over the difference between extended lunar and Martian mission spacesuits and the current state-of-the-art EMU, XEMU spacesuits. Then I'll be going into kind of custom-sized spacesuits and how that might solve some of the issues that we expect to arise. And then robotic testing devices for spacesuits, and finally with the Mars joint tester, which we developed here at UND. So first, a little bit of background on Martian spacesuit. A Martian spacesuit. So for a short Martian mission, less than 6 months duration on the surface of Mars, they'll still do an excess of 25 EVAs, and this will be important. I'll touch on this in a moment. The crew is going to be small, probably 4 to 7 individuals, picked years in advance, so the spacesuits could be made to those individuals. And extensive planetary EVAs. These EVAs will be on the surface of Mars, so the spacesuits will have to contend with the Martian regolith and the atmosphere, which will degrade the spacesuits much more rapidly than a microgravity situation. A Martian settlement, so that would be of an indefinite duration, so the individual will be on the surface of Mars for much longer than 6 months. Extensive planetary EVAs. Every time they go outside, they're going to be wearing their spacesuit. And so the spacesuits will need to be serviced on site and potentially even manufactured there, depending on how far out you look. So compare this to our current state of the art for the American spacesuit, which is the EMU and soon the XEMU, and hopefully 2023. The EMU must be refurbished after 10 to 15 years or 25 EVAs. So going back to the previous, the Martian requirements, this is not adequate. But even then, the suit would be a single-use suit just for that particular mission. The current spacesuit is modular, so that means it's a combination of a number of parts that are off the shelf, quote unquote, and then combined to fit the individual. And so the majority of the spacesuit research up to this point has been for microgravity EVAs. We've had an excess of 400 EVAs in microgravity, but only 14 planetary EVAs, which are part of the Apollo space program. EVA is extravehicular activities, so when you leave the spacecraft and operate outside. So the ISS has a low EVA load compared to the Martian or lunar mission. So the point of going to Mars or the moon is to go outside and perform experiments, as opposed to the ISS, which is an orbiting laboratory where EVA is used for maintenance and some experimentation, but typically to maintain and upgrade the laboratory. So here's a schematic for the Shuttle Emu. So this number of sized components has been reduced somewhat, but you can see here there's a number of components that are differently sized and then combined to fit the individual. So some issues looking forward to, so one thing to note is they have a stock of all these components on the ISS, and potentially if they use a modular sizing system for a planetary base, they would have to maintain a stock of all these components as well. Looking forward to a planetary spacesuit. Right now, there's 10 possible EMU arm configurations, as well as 32 glove sizes. Compared that to the 2 possible EMU leg configurations. When this is indicative of the current situation in which spacesuits are used, primarily in microgravity, where you're manipulating things and moving yourself around with your arms, whereas a planetary situation, you're going to be moving with your legs a great deal more. So it's likely that the spacesuit legs will increase in complexity, leading to increased number of components that will be needed to outfit a properly sized suit to an individual. So this kind of points to an idea that custom sized suits may make sense for these longer duration missions. Some of the cons are the inventory complexity. So for the Apollo missions, each astronaut had 3 suits, 1 to train, 1 to fly, and then 1 backup. Manufacturing complexity, the individual needs to be sized, the patterns need to be drafted for that individual, and then the suit needs to be made and then potentially modified specifically for that person. So that's potentially wasteful. If that person doesn't fly, those suits won't be used. So from that point of view, modular spacesuit is beneficial. But I've had conversations with astronauts point out how comfortable custom-sized spacesuits are. I had one individual note that the Sokol suit, which is a custom-sized IVA suit, was the most comfortable suit she's ever worn. Safety is also an issue. If we look at the statistics for the neutral buoyancy lab, something like 60% of the individuals who train in the neutral buoyancy lab have some sort of shoulder issues, and a non-insignificant portion of those lead to surgery to solve that issue. So a custom-sized spacesuit may potentially be safer to use. Finally, increased mobility. If the suit is sized to the individual, it's conceivable that it'll be easier to operate the suit on the lunar or Martian surface, increasing the astronaut's ability to perform his or her tasks. And so that's kind of the research question I would like to look at in the near future. Moving on from there, different testing methods have been used to kind of quantify how difficult it is to move in a spacesuit. So during the Constellation program, this is the setup that they used. Constellation was a lunar program before Artemis that was discontinued. So they attached an accelerometer and a load cell to the spacesuit limb, and then they actuated it throughout its range of motion. They recorded the accelerometer data as well as the load data, and they used that to map the torque required to move the joint to the position of the joint. And they plotted that as a torque curve, specifying how hard it is to move a joint throughout a range of motion. The robotic spacesuit tester was developed for a similar function. This is a hydraulically powered robot mannequin that was used to test spacesuit joints. So the hydraulic system was used to move the spacesuit joints, creating a force that was measured through strain gauges, and the potentiometers measured the angle at which the limbs are moved to. This had some moderate sizing capability. I think, to my knowledge, it was able to change length a small amount, but other than that, it was pretty one size fits all. Let's see. New York University developed a anthropomorphic robotic glove tester. So this is a robotic testing system that would be placed inside a pressurized glove. So when the glove was pressurized, they would be able to move the fingers using servos. And this, when you activate the servo, it would pull a certain amount of current, and that current was directly proportional to the torque required, or the torque load directed to that servo. And so I kind of thought that was an interesting idea, and I developed my device off of that. So this is presenting what was developed at the UND's Human Spacesuit Laboratory. So it's the Modular Anthropomorphic Robotic Spacesuit Joint Tester. So this tester accommodates a wide variety of size limbs. So the robotic arm can be sized to a number of individuals. And beyond that, the spacesuit components can be sized so you can test the effect of the spacesuit component size relative to the size of the individual. The robotic arm is anthropomorphic, so that means it's shaped more like a human limb as opposed to the previous testing systems. And this will allow for a more realistic spacesuit astronaut interaction, allowing us to really look at how the spacesuit sizing affects the torque requirements of moving the spacesuit limb. Commercial off-the-shelf electronics were used to keep the cost low and allow this to be built pretty much anywhere that has a 3D printer and some shop tools. Here's a demo video of the device working. So on the left is a pressurized spacesuit arm assembly. On the right, you see the bare robotic arm moving through its range of motion. Yep. Okay. Oh. All right. So here I'd like to talk about the disconnect design. So one of the things that's important about this device is it can be used with a number of different size disconnects. So the disconnects fit onto the pressurization interface of the robotic arm tester. And the disconnect also drives the rest of the geometry for the spacesuit arm. So a larger disconnect will necessitate a larger diameter spacesuit joint. Whereas if you can reduce the size of the disconnect, you'll reduce the size of the joint and potentially reduce the torque requirements needed to flex that limb. Yep. So kind of in conjunction with the resizable disconnects, there's a resizable arm that's been designed. This is an anthropomorphic robotic arm, so it's shaped like a human limb, and it's sizable to the 99th percentile male and the 5th percentile female. So this can accommodate a wide variety of range of sizes. So you can look at, you know, say what a very small female, how that arm interacts with a joint, whereas you know, you can look at the changes in the individual's physiology and see how that affects the how difficult it is to move a spacesuit joint. Here's the mechanical drive system of the robotic arm. So starting from the right, there's a drive gear. This is driven by a servo, and I'll talk about the electronics in a minute. Connected to the drive gear is a cable loop. So the cable loop runs all the way through to the forearm, and attached on the cables are pistons, and these pistons fit inside a gasket. So the left side of this diagram could be pressurized, providing the pressure to replicate a spacesuit limb in use, whereas the right side isn't pressurized above ambient pressure, allowing for a pressure differential. Here is the low-cost electronic setup that was used, starting from the gear, the drive gear, which is between those blue brackets. I used a high torque servo, and I rerouted the potentiometer of that servo directly to the elbow of the joint, so you could take a direct measurement of the elbow, the angle of the forearm and the upper arm. These power cables of the servo were routed through a current sensor. So we were able to sense the current draw of the servo and then back calculate the torque requirement of the joint from that. All this is operated by a Raspberry Pi with a servo controller and a simple Python script that would run the servo through the range of motion while recording the current. Here's the data collection. So on the left is an unpressurized test where the spacesuit joint was moved through the range of motion without any pressure. And on the right is the same test where it's pressurized. And so one thing to note is the difference between the two. So the device was easily able to measure the increased current draw of the servo due to the increased torque requirement due to the pressurization of the spacesuit limb. Okay, so conclusion. So given the duration of extended lunar and Martian missions, spacesuits will only last one mission. And so looking, because of that, custom suits start to make a little bit more sense, but more work needs to be done to really figure out the costs and the benefits of a custom size suit system. So new technology needs to be developed to kind of test and design these custom size spacesuits. And the Mars Joint Tester kind of fills this niche where it allows the custom size or the individual limbs to be replicated and then evaluated inside a wide range of spacesuit components. Here's some citations, specifically some of the photos on this presentation were retrieved from these works. Any questions? I guess I finished a little bit early, sorry.
That's all right. Thanks, Will. That was a great presentation. If any of our, we have a question from Linda. She asks, does the drag of the pressure seals on the cable affect the reading? Let me, just before you answer that, let me just say to our audience members, if you have any questions, please post them in the chat window and we'll ask them for Will.
Sure, yeah. So it does to a certain amount. And so that's why one of the things when this is actually used is we'll, kind of take that into account and perform a dry run, so we can kind of see the biases in the system, which we can remove later on and kind of account for that.
Cool.
But it's a moderate, it's a small effect compared to the pressurized limb forces.
Sorry about the background noise. Mike asks, is the parametric disconnect design something that was developed in-house or based on an existing design?
Yep, that's developed in-house. So we have a number of spacesuits here, and so we were kind of looking at, creating a way to have a disconnect glove for easier donning and doffing of the spacesuits. So we already had it designed, and so I kind of, took it and applied it to this project as well. Yeah.
Atash asks, could the suits have servos added to help the wearer move around?
Yeah, so exoskeletons and spacesuits is a topic that comes up very frequently. I think the big issue is spacesuits are going to see a lot of wear and tear. And if you're relying on an electronic system for them to operate, that's you're introducing many ways for the spacesuit to fail that aren't there at the moment. So I think what instead we should really focus on is developing spacesuits that can be simple, serviceable, and as simple as possible. Because if it breaks on the surface of Mars, that's a long way away.
You talked a little bit earlier about having stores of replacement parts to repair suits. Is that, do you think that there's a balance between that versus manufacturing replacement parts in place with 3D or milling technology?
Well, so let me just plug my research a little bit here. So right now I'm working on a 3D printed spacesuit. We recently got a grant for that. So I'm leaning towards 3D printed spacesuits naturally, but I think for the first few missions, you know, 3D printed spacesuits won't be, or in situ manufactured spacesuits won't be a proven technology. So I think conventional spacesuits will be required for the foreseeable future. But for a, you know, say a Mars settlement, that's when in situ manufacturing is really going to be important, especially with, you know, replacement parts.
Cool. Elaine asks, do materials used block space radiation? What materials are they?
Yeah. There is some shielding, but it's not nearly as much as if you're, say, inside a spacecraft. So the spacesuit has a bunch of different layers. The outer layer is a specialty fabric called ortholayer. Under that is some mylar, which is kind of like chip bags. Then there's nylon, TPU impregnated nylon. But so it's, you have some shielding, but not nearly enough to really, you know, properly shield an individual. Yeah.
Thank you. Just as a reminder to our participants, will you please make sure that your microphones are muted? Andrew asks, how do rotating joints maintain pressure?
Okay, so I guess he's talking about bearings. So there's gas-type bearings that they developed. And one of the things that they're developing for the lunar mission is dust-tolerant bearings. So the bearings on the Apollo suits, or bearings are a huge failure point, specifically when the dust infiltrates in. And so those would wear out very quickly. So they're gas-type bearings. They have a seal in them.
All right. Mike asks, what are the top 3 technologies that you think would be most assistive to space technology?
Gotcha. Let's see. Well, if you can figure out how to a higher pressure joints. So right now the spacesuit is run at about 4.3 pounds per square inch of pressure. And so the issue is the habitat is, or the ISS is kept at atmospheric or standard atmospheric pressure. So that's about 15. So when you drop down from that high pressure to the low pressure, that takes a long amount of time. And so they have to do what's called a pre-breathe, which actually takes a couple hours. And so you're sitting in the suit for a couple hours, and then you know, you're in it for a couple hours, and then you finally get to go do your work, and then you come back in. So a higher pressure system will allow the astronaut to get in and out of his or her suit, which increases the operational capability of the suit system. So a higher pressure, let's see, the suit port system, which once again, that's when you can dock the spacesuit to a habitat or a rover and get in through the back hatch. So once again, that simplifies the system. You don't need an airlock necessarily, and the dust can stay on the outside of the space habitat or rover. So higher pressure, suit port, and let's see, dust mitigation. So if you can create a spacesuit that can operate in a dusty environment, that's really important. The lunar spacesuits were almost, you know, they couldn't have operated much longer than they did, which at most was, you know, a little over a day on the lunar surface. So dust is going to be a huge issue moving forward. And there's a lot of work going on there. So there.
I thought you were going to say toilets in the spacesuits.
Oh, yeah.
Let's see. Oh, you mentioned increasing the pressure tolerance of the joints. What are some ways that that are being explored to increase that tolerance?
Sure, sure. Well, so the typical, so the current joint is kind of created in what's called a flat pattern. So that's a number of fabric pieces that are flat, and then they're sewn together or welded together in terms of the bladder material. But moving towards some other joint design, maybe like a bellows, which is kind of like an accordion-shaped spacesuit joint, might be beneficial, but it has some complexity to it. So there's been quite a bit of work, but none has really cracked the code on how to really make a higher pressure suit work effectively.
Thanks. Let's see. Beverly asks, how heavy are spacesuits?
It depends on the spacesuit. So we have a couple of different prototypes in the lab here. So our Martian prototype spacesuit, the NDX-1, weighs about 50 pounds, but that's without the life support system. So depending on the life support system, it's probably going to weigh over 100 pounds on Earth. But when you move to a lunar or Martian environment, the gravity is going to be reduced somewhat. So that's going to be less of an issue.
Let's see. Finch asks, and this is probably a big question in your mind, is there a stable career in parametric design?
A stable career?
Yes.
Oh, yes. Well, I think, so it's CAD. And so pretty much being able to, create these complex CAD systems where you can input a number of numbers and have it spit out the finished part. I think there's definitely a career in computer-aided drafting and design. And this is kind of a higher level technique that if you can figure out how to do it, you can definitely talk about it at job interviews. Yeah.
Let's see. Neil asks, did the lunar missions anticipate the dust issues that you mentioned, or was that a new finding?
Yeah, so they knew a little bit about dust, but they had no idea it was going to be nearly as bad as it was. So dust is electrically charged by solar radiation and kind of different energizing sources. And so it's statically charged. So it clings to literally everything, or all of the tools and the suits that they were using. And so even when the astronauts entered back into the lunar excursion module and they removed their spacesuit, you can see that their faces are just covered in this. And it gunked up all the systems. And they had no idea it was going to be as bad as it was. So it's definitely something that's being looked at as we go back.
Very interesting. Stefano asks, if a spacesuit gets damaged while in use, is the astronaut doomed, or do they have some kind of repair kit?
I think I don't know if they have any repair kit. Well, it depends on the type of failure. So there's been cuts on the gloves of the spacesuit due to. So there's handrails on the International Space Station, and those can get hit by micrometeoroids and create sharp edges. And so those sharp edges have cut gloves before. And so that just caused a small leak, and they needed to end the EVA early so they could go in and deal with that issue. If it's a major leak, say if you have the whole, if your glove pops off or something like that, I think your chances aren't looking too good. Yeah.
All right, I think we have time for one more question, then I think everybody wants to get to the next speaker.
Sure.
Atash asks, what about skin-tight gasless suits? Are they possible? I think he's talking about mechanical counterpressure suits.
Sure.
Can you talk about that?
Yeah, yep. So that's a fascinating part of spacesuit research. The current issue is convex surfaces. So like the inside of your elbow. So you can't really have, so you can't really have tension element filling in the convex surface. So you'd need to have something there that kind of pushes down, but it's an ongoing issue. Along with that, there's also different anatomical features that would be difficult to cover in a line of non-extension setup, which I'll leave to your imagination.
Yeah, I won't ask you to elaborate on that, but as far as having adaptive flexibility with those concave areas, are you familiar with piezoelectric materials? And
Oh,
fabrics?
sure. Yep, yep.
Is there any potential for those to be used?
I think Dava Newman at Professor Dava Newman at MIT is doing some work there. I read some of her work, and I assume she knows, she has a way of working around it, but I haven't really figured out exactly what she's planning on doing there.
Well, that will be something for us to all look forward to. That
Yeah.
sounds very interesting. Well, I'm going to go ahead and cut things off here because I think everybody wants to get going. But thank you very much. That was an excellent presentation.
Cool. Thank you. I appreciate it.
Yep, you're welcome.
Thanks, everyone.